So, good morning, everybody. I can see that there are 375 of you so far. So people are still trickling in. The time is now 11:10. It's a beautiful day for a bike ride this morning. It was a bit of a late night last night because we had that midterm, and then I sat up for the alternate sitting, and then after each midterm, there was a lot of discussion with people who were having trouble uploading. I would say about 90% of you didn't have trouble uploading, but then there was a 10% that really had a lot of trouble. So that's a lot of people. So I'm not sure. So definitely the next midterm, I can't remember the date, but this is midterm 3. We'll go back to just multiple choice. And maybe we'll only do multiple choice from now on if this is a complete disaster. But I have some tricks up my sleeve. There's something called CrowdMark. I don't know if you've ever used that for math, but maybe I might try that to see if upload's going any smoother. Let me share my screen here. We can talk about what we're going to do today. So here's the plan. The plan is we're going to review the last night's midterm assessment questions. Then we're going to talk about radial acceleration, which I've previously called centripetal acceleration, but I think it's better to call it radial. It just means it's in towards the inward radius of a circle. We're going to talk about vertical circular motion. I'm going to swing a bucket of water over my head if there's time. And then I want to talk about banked curves, which is what is in this picture. And let me make sure I have my lists up, participant lists. Victoria, did you have a question before we get going?
Hello.
Hi.
Hi, Professor. Actually, the question I have has to do with the midterm. So I know that this is now the lecture session. So I'm
just about to talk about the midterm, actually.
Oh, perfect. Okay. So it actually has to do just, I took a shot of the, I took a photo of the question 1, and I was kind of speeding through.
Okay, so you know what? I'm sorry, Victoria, I'm just going to cut you off really quick. Basically because I'm really happy to talk with you about, individual issues with your midterm. Like, for example, it sounded like you were going to talk about your own upload or something. For the lecture, I just want to talk about the physics. And so I think the best step here is we should go through the solutions, and then I'll open it up to questions about the physics of these questions. And if there's anything about Quarkus or uploading or taking images or photographs or anything, I do want to talk about that, just not during this particular 50 minutes. So there were 796 students wrote the second midterm last night, and we got all your images. There was some, if you emailed your images to me, that's also going to be uploaded if it was in time. I have emailed my TAs who will be working on marking your questions this week. And so what I'm going to show you right now is the same rubric that I gave to them. My hope is that they will be done by Friday. If not, maybe Monday. We'll see how the marking goes this time. So the first question was about a crate. A crate with a mass of 35 kilograms rests on a horizontal surface. Trouble seeing this. The coefficients of friction between the crate are mu sub the static friction coefficient of friction is 0.5, and the kinetic coefficient of friction is 0.2. A person pushes on the crate with a force of magnitude 150 newtons at an angle of 35 degrees below the horizontal. So that's what I tried to draw there, where this would be like your 35 degrees, which I'm going to call theta. What is the magnitude of the acceleration of the crate? So I've tried to draw just sort of the variables. I'm going to define the system as the crate, and then S is the surface down there. I think it's going to be sliding along. If this is acceleration, then it may also be moving with the velocity to the right. So in my next step, I'm going to assume that we have kinetic friction. The thing is sliding. So the box is sliding to the right. Probably if it's accelerating towards the right, maybe it's also moving towards the right. So that means that the kinetic friction force is to the left. So here I've drawn what I think are the 4 forces acting on this crate. There's the pushing force of the person on the crate. There's the normal and kinetic friction forces of the surface on the crate. And there's the gravity force of the earth in the crate. And since it's accelerating towards the right, I'm going to define the x-axis is to the right in the direction of the acceleration, and the y-axis in the up direction where it's not accelerating. So there's going to be one diagonal force, which is the pushing force. Yeah, and so the acceleration in the y direction is 0, so you have to balance the y components of the forces. You've got normal minus gravity minus f sine theta equals 0, so that means you can solve out for the normal force. The sum of the forces in the x direction gives you the a acceleration you're trying to find. So it's 1 over mass times f cos theta minus fk. K has an equation which is mu sub k times n. We already solved for n from the balancing the y forces. So you just plug it in and you get this big long equation. And that's 2 points for that. And then lastly, plugging in the numbers, and I got plus 1.1 meters per second squared. So, which is good. It's sliding to the right and it's accelerating to the right as well. So it's not only sliding along, but it's speeding up. So this all works out. So that was one solution. And the way I did that is I assumed that the crate was already sliding. So you maybe you might have thought, since it's rests on a horizontal surface, maybe it was at rest at first. And so there is a whole other solution you can do. It starts the same with the sketch and translate. You've got the same exact situation. You're asked to find the acceleration. You've got 2 coefficients there. System should be the crate. But here's where this solution might differ. And this is also a perfectly acceptable solution, is that let's assume the crate starts at rest. That is a different assumption. So it will give you possibly a different solution, which is fine. This is one of the main themes of the Etkina book, is that if a question is a little ambiguous and doesn't state everything very specifically, then you have to make assumptions. And so I originally, when I solved this, I made the assumption it was already sliding, but it doesn't really say that. It said rests on a horizontal surface. That could mean it's at rest or it's just on a horizontal surface. I don't know. So you have to state what it means. If you state that the crate starts at rest, no problem. Static friction might keep it at rest if the static friction is less than Fs max. So all we have to do is just figure out which is bigger, Fs or Fs max. So here's the force diagram. There's the static friction force, define y, x that way. Again, the diagonal force is the pushing force. So here, again, exactly the same equation by balancing the y forces. You get normal forces mg plus f sine theta. When you balance your x forces, now we have static friction keeping it at rest. Then you would get Fs equals F cos theta. And then Fs max has a different equation for it. So you have 2 equations. This equation for static friction force, which is self-adjusting, as you might remember, and this equation for the maximum static friction force. And so the question is, if we compare these 2 numbers, which one is bigger? So I did that in the next step, which is Fs turned out to be 122.9 newtons. Fs max turned out to be 214 newtons. So it's absolutely acceptable that this thing could just stay still. You're not giving it enough force to get it going. So the answer is that the acceleration is 0. And it turns out if you wrote, I posted all this on the website, but if you wrote the alternate sitting in which you're pulling on the crate, you get the same answer. There's the static friction force that's required to keep it at rest is less than the maximum static friction force, which you find by mu sub s times the normal force. So why don't I open it up before I do the next question? Why don't I just see if you guys have any questions about that first one about the crate? Thea, how's it going?
Hi.
Hey.
Questions because I'm writing the alternate setting too. And I saw in your PowerPoint that it says it's push, but my question is pull instead of pushes. So I was wondering.
So it's a different solution. So yeah, if you have questions about the alternate sitting, then you can just go onto the website and look at that solution. It's very similar, but obviously it's going to be a little different because your force diagram will be different and all that stuff. So does anyone have any questions about the main sitting, this question that I just did, or Bardia?
Hi, sir. Can you hear
Hi.
me?
Yes, I can. Yeah.
I have a question about how you actually perceive the question.
Yeah.
Because to be honest, during the test, I was kind of like confused with the fact that says the angle 35 degrees below the horizontal.
Yes. Yeah. Yeah.
So I was thinking that maybe you're actually pushing under the box, like with 35 degrees under the horizontal. Like, can you bring it to the first graph?
Yeah.
So you see this, there's an arrow from the top, you're pushing it.
Yeah,
What if
yeah.
you're actually pushing from underneath with 35 degrees, so you
From
actually
below.
decrease the friction force?
With a magnitude of 150 newtons at an angle of, so yeah, I see what you're saying, but I think the best way to think of this is that I'm trying to describe a vector. So the vector magnitude is 150 newtons, and the vector direction is theta equals 35 degrees below the horizontal. So that's the force that the person pushes upon the crate. Yeah, I see what you're saying, is that maybe if I had said the person is 35 degrees below the crate or something, below the horizontal of the crate, then you would have a force that's 35 degrees above the horizontal, but I don't think that's going to be accepted. But it's still, again, this is the nice thing. If you show your work and show all your steps in here, you're going to get all kinds of partial credit for doing something correctly. You'll probably just get actually the same answer as you would get for the alternate setting if you did it properly. So thanks for that. Hamad, did you have a question about this crate thing?
Yes, so my question is, like, it says that the crate is at rest, right? So, and
it doesn't really. It says, just to interrupt you, sorry, it says a crate with a mass of 35 kilogram rests on a horizontal surface. So it could be at rest, I guess. Maybe you might interpret that, which is fine. It just, you have to state more clearly, is it, if it starts at rest or doesn't. It doesn't say, I don't think.
So if we didn't write that we assume that the crate is at rest, we lose marks?
Well, you have to state your assumptions, I guess. I don't know. Yeah. I mean, it's 0.5 of the mark for, which one is it? It's under simplifying diagram. It says to state all of your assumptions. So you're saying it's not an assumption because you think that the question stated very clearly that it started at rest?
Yep.
Okay. Again, so yeah, it's a little hard for me. It rests on a horizontal surface. You don't think it's possible to rest on a horizontal surface and be moving? Because it has the word rest in it.
I mean, it's not on an inclined surface, so I'm not sure.
Well, yeah, it's definitely a horizontal surface, but this is sort of an English question, right? Something rests on a surface. Are you able to rest on a surface and be sliding along? Maybe not. So hopefully you stated some assumptions, because you are required to state some of your assumptions, like no air resistance or something.
I mentioned like the string is not stretched, but then I didn't mention it's at rest.
Not stretched. Okay.
It's like for
I mean,
like
I
I
can
was
talk
doing.
to my markers about that. That's a bit of an odd one. But thank you. Again, there's all these hands. Yikong, did you have a comment or question about this crate question?
Yes, Professor.
Hey.
So I wrote my final answer in 3 significant figures. Is that
that's wrong, because I think the coefficient of kinetic friction has 2 significant figures, right?
So that's going to be like 0.5 deduction?
Yeah, I think so. You got to go with the least number. Nicola?
Yeah. Hi. I have a question for the static, the one where you mentioned the static friction. I compared the maximum static friction to the horizontal force applied by the person. Would that still be the same effect of the answer, or no?
I'm not really sure. So there's the issue is you got to be a bit careful with your components, right? Because the person is applying this force on a diagonal. So part of the person's force will increase the normal force or decrease it if you're pulling. And then part of the component of that force does have to get balanced by the static frictions. Could be a little careful there.
For the FS max, I compared it basically to the X component of the pushing force, the X component of the pushing force, compared to the maximum static friction. That's what I compared.
Yeah, that's what I did, right? Isn't that what I did?
Well, yeah, you just said you compared, like, you basically just said compare the FS to the FS max. I said compare the X direction of the horizontal. Would that still be the same thing?
Oh, I see. Yeah, I think so. Except, yeah, that's right, because I'm comparing FS where that's what I've written though, right? This is what you're saying. That is.
Oh yeah. Oh, actually, I actually missed that part. Sorry, but yeah, but instead of calling it FS, I said I'm comparing whatever the F in the X direction compared to FS max.
Yeah, yeah, I think you're doing the exact same thing, so that should be good.
Okay. All right. Thank you.
Yeah, sure. Okay. Awesome. I think what I want to do is go through this projectile motion question really quickly, and then we can kind of move on here. Grasshopper. So, grasshopper leaps into the air from the edge of a vertical cliff. As shown, the grasshopper's initial velocity is 1.34 meters per second squared, 50 degrees above the horizontal. The grasshopper lands on the flat ground, a horizontal distance of 1.17 meters from the base of the cliff. I think it doesn't really show that here, but it did on the diagram. The question is, what is the height of the cliff? So my first step was to kind of sketch it out, write down all my knowns and unknowns. X is the, what is the unknown here? What is the height of the cliff? Yeah, H. This is what we're trying to find. Put a question mark beside that. I guess an assumption you could make here is assume no air resistance. That's kind of an important thing. I think probably a grasshopper would have some air resistance on it, but you can't solve the problem that way. So we're going to just assume what happens if there's no air resistance. It's a very aerodynamic little grasshopper. So maybe this should be a motion diagram or something. But anyway, some dots go up, some dots go down. You've got the X component of the velocity is constant, X over T. And then the Y component of the acceleration is downward 9.8 meters per second squared. So I have defined Y to be up and X to be to the left. You could define, or to the right, you could define Y to be down and X to the right if you want, in which case A sub Y would be plus 9.8. Either way is fine. So then I set up my equations. Basically, you can use, the way I did it is I used the X component to solve out for T, and then I used this equation for the Y component, Y0 plus V0 YT plus 1/2 AT squared. And then I plugged in your T from the X component into here and here. And it was a lot of math, but it ended up working out. I got an equation, I plugged in the numbers, and I got Y equals negative 7.65. And what I didn't really mention here is that I assumed that the origin of my coordinate system was where the grasshopper stopped. So he ends up 7.65 meters below where he started. It's a little hard to evaluate whether that seems right. It seems like a long way for a grasshopper, but at least it's negative. I think maybe that's one way of evaluating it. So the height of the cliff would be 7.65. That's what I got. That only had one solution, I think. And then, of course, so I'm going to open up the questions, but if you have written the alternate sitting of the midterm last night, which around 100 of you did, then you would have different numbers. So I think the math and the solution should be about the same, but you might see that you have slightly different numbers. So all you have to do is go on to the course website, go to module 2, and you will see that I've posted everything that I've posted here is already posted there, and you have your own version for alternate sitting. So if you haven't, just gonna, Arpit, how's it going?
Hello, Professor.
Yes, hi.
Yeah, I just wanted to ask a question regarding like the personal issues we faced during uploading. Where can we talk about this and like
we can definitely. So once again, I'm going to cut you off right there. I do want to talk about that stuff, but while we're recording a 50-minute lecture, I don't think it's really a best use of our time here. It's an issue. Certainly, I spent about 2 hours talking about these issues last night with students, and I talked about it with April Seeley. I've talked about it with Stephen Morris, a colleague of mine who also ran a test in a different course last night. Same sort of issues with about 10 students. Again, it's about 10% of students seem to be having trouble with the upload, and 90% seem to it just uploads and fine. So that's too much. That's not good enough. I think that 100% of you should be able to upload it just fine. So I would like to find a different way of doing test 4, and I'll be looking into that for sure. And then again, if you have something more you want to talk about, let's talk about it just after class. Thank you. Osaze, any physics questions maybe?
Oh, hi, Professor. Sorry about that. I actually had my hand up for the question before, but
okay.
You had answered it. So sorry about that.
Okay, no problem. Yeah, you have to remember to lower your hand sometimes. Ishmael?
Hello, Professor.
Hi.
So I had a question on your, the rubrics. Like, I have seen the solutions, and like, are the markings, based on each individual boxes? Like for the sketch, it's 2 marks for the like, even if the solution's wrong, like height of the cliff is wrong.
Yeah, no, that's right. So even if at the very end, the height of the cliff is wrong, that's only 2 points of it. You can already get the 6 as long as you did the steps 1, step 2, step 3 correctly, right? So you get points for doing each step correctly.
Oh, it's a gradual process.
Yeah.
Okay. Thank you, Professor.
Okay. Yeah, you're welcome. Heyman? Not sure if I'm pronouncing that right, but.
Hello, Mr. Harlow. Can you hear me?
Yes, I can. Yeah.
So for the question to in 8:10 p.m. I used a different equation, and I slightly got a different number. And the equation that I used was first I found a velocity initial for horizontal and initial. And vertical. Then I plug them in an equation of y equals y0 plus v0 one of the equation, and I got 10.47 meters for height. And so like I did you see in the Pearson summary part, the Pearson textbook, there are few projectile motion equations.
Yeah.
And I used only to use those 2 of those equations to find the answer. And I clearly found out what is the variable that I'm looking for and what are the knowns, and I got 10.47.
Okay. So that's interesting. So I think there's only one answer. There's one height of the cliff if you neglect air resistance, right? Now, there are lots of different ways of getting to that answer. But if you've gotten the wrong numerical answer at the end, that indicates to me that you've used a wrong equation somewhere. Maybe, you've started at a wrong height or something. Maybe you found the difference between the top height and the bottom or something. I'm not sure. But the grasshopper starts at the edge of the cliff. It goes up. We're not computing how high it goes up, actually. We're just waiting for it to come all the way back down to the bottom and finding the difference between the initial and the final. So it could be that it's something to do with that. I'm not really sure. All right, I've just noticed that things are going completely nuts on the chat window. Cutting you guys off. So the answers for the alternate setting are sitting there on module 2 on the Quirkus. Okay, I'm going to move right along here, I think. I want to talk a little bit about uniform circular motion. And they do these experiments I guess there's a few different observational experiments and analyses that they talk about in the textbook that get you to this radial acceleration equation. And so the first one is we have an object which is moving, I call it uniform circular motion. It's moving on a circular path at a constant speed. And here at the top, it's got some velocity v. And what they're going to compare is how does the velocity change going from initial to final? Well, initially, here it was going up like that and at a constant speed, but at a different direction. And finally, it was going down in diagonal. And if you take delta v is equal to v final minus v initial, then you get delta v is down. Does that make sense? So at this point, the change in velocity is down. Okay, so that's called radial acceleration. We talked about that before. If you increase the speed, then you increase both of these initial and final velocity vectors that you're adding. So an object moves in the same circle at a constant speed that is twice as fast as experiment 1. This delta v will be twice as big as the delta v from before. And if it's 3 times the speed, you get 3 times. So from the observational experiment, it is concluded that the magnitude of the radial acceleration is proportional to the speed squared. I missed something actually. Not only is delta v bigger, but since it's going faster, delta t is smaller. It takes half the amount of time for it to go from the initial point to the final point. So you've increased delta v by a factor of 2, and you've decreased the denominator by a factor of 2 as well. So delta v is 4 times larger. Okay. And then if you go to 3 times, then delta v is 9 times larger. So that's what they're getting at there. Radial acceleration is proportional to the speed squared. And then the last one is dependence of acceleration on radius. So experiment 1, an object moves in a circle of radius r at a speed v. Choose 2 points in the circle and examine the velocity change from the initial to the final location. Okay, initial to final. Delta v divided by delta t1 is equal to the acceleration. Experiment 2 would be an object moves in a circle that's twice as big, but at that same speed v as the previous one. Choose 2 points so the velocity change is the same as in experiment 1. This occurs if the radii drawn to the location of the object at the initial position and the final position make the same angle as in experiment 1. To have the same velocity change as in experiment 1, the object has to travel twice the distance because this radius is twice as long. Same angle, but now you're farther away, so you're going to go twice as far here. Since the speed of the object is the same as in the first experiment, it takes the object twice as long to travel that distance. So you've got 2t on the bottom. So this is as half the acceleration. So acceleration sub r is a half of before. What that means is that the magnitude of radial acceleration is inversely proportional to the radius of the circle. If you go in a bigger circle, there's less acceleration needed for the same speed. So when you combine these two proportionalities, you get v squared over r. With the constant of proportionality being 1, a mathematical equation is derived. Radial acceleration. For an object moving at a constant speed v on a circular path of magnitude of radius r, the magnitude of the radial acceleration is a sub r. And the direction doesn't say here, direction of a sub r with an arrow on it is toward the center of the circular path. A little behind. It's okay. So let's do a quick poll here. Okay. A ball is whirled on a string in a vertical circle. As it is going around, the tension in the string is here. A, greatest at the top of the circle, at the top of the motion. B, it is constant. C, greatest at the bottom of the motion, or D, greatest somewhere in between the top and the bottom? So we're asking about the tension in the string. Then we're going to try something like this. Okay. So 82% of you clicked in. So if the rest of you could just give me your gut feeling. 5, 4, 3, 2, 1. Sharing results. So the most popular answer is C, and I actually like that as well. So here's what I think. It's a bit tricky, this one. As the ball goes around the circle, it must be accelerating towards the center. That's the A sub r. A combination of gravity and tension must provide the inward radial force necessary to give it this, whatever the radial acceleration is, v squared over r. At the bottom of the motion, if you're down here, for example, then the force diagram is going to be Fg of the earth on the ball, and upwards will be tension of the rope on the ball, and the acceleration, A sub r, is upwards at the bottom. Gravity acts in exactly the wrong direction, so tension must be greater in order to counter it. Whereas if you've got it up here, this ball up here, then tension and F sub g are both acting together, both in the same direction, and so the tension is less at the top of the path because some of the force needed to give it that v squared over r is provided by gravity. And then there's another thing, which is that I would think also the ball might be moving faster at the bottom than it is at the top. It doesn't necessarily have to be uniform circular motion. And so in that case, here's my phone. You've got not only is, even if it was uniform circular motion with the same v squared over r, you'd have more force at the bottom because you're countering gravity, more tension force. But if that would be even more if the v squared over r was also greater, then you'd need even more tension. So I want to do a demo here. Oh, this is a little note about a fictitious force called centrifugal force. If you're in a car and it turns a corner quickly, you feel thrown against the door. And I remember this very clearly from when I was a kid, sitting in the back seat with my sister, is that if you were turning if one of my parents was turning the car really quickly, then we'd get pressed up against each other. There was no seatbelts back in those days. That's a long time ago. You feel like you're getting thrown against the outside of the curve. So that's actually opposite to A sub r, the radial force. This is a fictitious force. It's called the centrifugal force. It helps you to describe your experience relative to a non-inertial frame. What's really happening is that by Newton's first law, you are trying to continue in a constant velocity in a straight line. But then the door is providing an external force, normal force on you, which is towards the center of the circle. This is where this A sub r is coming. This is gives A sub r towards the center. And so in the inertial frame of the ground, the only real force here, which is pressing on you, is actually towards the center of the circle. It's very similar to fictitious forces we talked about before. Okay, so there's something about the minimum speed of water here. So I'm going to swing a bucket of water over my head. The other thing that I want to do is take the microphone into the webcam just for a minute. Okay. So hopefully you guys can see me. Maybe I'll put it a little bit over here. What I've got, hello, is I got a bucket of water on a string. I got a bucket on a string, and I'm going to pour some water in it. So you can watch me do that. Get it about that full. And now I'm going to swing it over my head. Now, I've never done this before with this bucket. It's my first time with this experiment, but that's okay. I should have practiced maybe before, but who's got time for that, right? Let's try to hold it like this. Okay. You guys ready? Okay. And not a drop was spilled. Let's see if I can go. That was twice. Let me do it 3 times right now. So why doesn't it spill out of the top? It's fun. I'm going to put the microphone back on laptop and share the screen. Okay. So the basic idea with this one is that, and this is sort of the roller coaster loop-to-loop problem, is that if you've got, you can have a cart or a loop-to-loop where a cart is actually going on the inner surface of a circular path. And if it's going fast enough, the speed is greater than some minimum speed, then the normal force adds to the gravity to make it large, to make the force large enough so that the normal force plus the F sub G is equal to F sub R, which is going to be mass times V squared over R. The point is, just erase that actually, is that normal force must always be away from the surface. It can never be towards the surface unless the surface is covered in glue. So if you're just at the exact speed called V minimum, then there is no normal force that is needed. So you can actually kind of just leave the track. That's called V equals the minimum velocity. And if you go less than that, like if I actually spun the bucket at a slower velocity than V min, then what happens is that the gravity force is more than the centripetal force that's needed, or the radial force that's needed to accelerate it with A sub R. And so you can't have normal force pulling, right? Normal force can only push. So then the thing leaves the track, or the water would fall out of the bucket. So what I did is I was swinging that bucket fast enough so that the bottom of the bucket was putting a normal force on the water and actually holding it in there. So what the water wanted to do was continue going off in a straight line, but instead the bucket was pushing it in a tight circle. And so the water was just forced to stay in that circle. Same way the water wants to fall down when you're just holding it still, but the normal force of the bucket holds the water in by pushing upward on it. If you go in a fast enough circle, you've got that same situation. Normal force of the bucket on the water is pointing inwards, even at the top of the circle. And that's why it doesn't spill. So where are we here? Yeah, I'm not going to have time for this example at the end, but what I can do, I've got a couple more polls. Let me talk about self-adjusting forces. I've already talked about this a bit, but the basic idea is that you know the force of gravity is m times g. You know the kinetic friction force is mu sub k times the normal force. Okay. But normal force and tension and static friction are all self-adjusting forces. There are no equations for these. And the way I remember it is that the normal force is whatever is needed to keep the object from crashing through the surface. Tension is whatever is needed to keep the string from breaking. And static friction is whatever is needed to keep the surfaces from slipping relative to each other. In all of these three cases, if you're asked what those forces are, you have to draw your force diagram. We call it force diagram in this course, not free body, and figure out the forces by using Newton's second law. Let's do another poll here. A car is rolling over a hill at a constant speed v, which is shown there, or a constant velocity. The question is the normal force on the car is greater than the force of gravity? B, the normal force on the car is less than the force of gravity? Or C, the normal force on the car is equal in magnitude to the force of gravity? So we're comparing the magnitudes of the normal force and the gravity force. Or you can't tell any of these inequalities unless you know what the V is option D. Okay. Let me try to click in 5 seconds and I'll discuss this one. 3, 2, 1. See what people said here. 57% of you voted for C, that the normal force is equal to the gravity force. And 28% of you voted for B, that the normal force is less than the gravity force. And 11% of you voted for A, that the normal force is greater than the gravity force. So this was a pretty controversial one. So this is how I'm going to do this. Here's my sketch. If I'm going to solve this, what I need is system is equal to the car. And I'm going to say, let's draw a force diagram, which is just this, that you've got the normal force of the surface on the car, and you've got this gravity force, F sub g, of the Earth on the car. And is there an acceleration is the question. Well, yes. So I think that since this is a circular path that it's on, a little bit before the velocity was, this is before, I guess, V0, and then afterwards, V final, it's down like that. So this car is constantly accelerating towards the center of the circular path. So A sub R is down. So if we want to define plus R to be down in this case, then what you would have is that the sum, or A sub R, is the sum of forces in the R direction has got to be greater than 0. And that's going to be F sub G minus N, because I've defined R to be down towards the center of this thing, is greater than 0. And what this means is that F sub G is greater than normal force, or in other words, normal force is less than the gravity force. And so, and I kind of remember this, we had this, there was this hill, I used to live in Edmonton, and there was this really bumpy little hill, and my dad would drive towards it, and we'd go over this hill, and just as we were rounding the top of the hill, we felt kind of weightless, like the normal force was less on us. And so that's what that's the weight you feel, is this upward force of normal force on you. So if that goes down, you kind of feel it in your stomach a little bit. Now I want to do another quick poll. This is the same exact question, but now instead of going over a hill, you're going at the bottom of a valley. What do you think? Same exact question. How do you compare the normal force on you to the gravity force? Okay. I'm going to end up polling. A lot of you have answered. So 81% of you now believe that it is A, and that's the one that I liked as well. So here, what I've got is A sub R is going up because there's a circular path here which goes like this. So the center of that circle is somewhere above. So in the, radial acceleration is always inward towards the center of the circular path. And once again, so define, what I like to do is I define plus R to be up, and then the sum of the forces in the R direction, which has got to be greater than 0, is equal to, now it's, I gotta do that again here. Normal force is up, F sub G is down. Yeah, so it's normal minus F sub G. So normal minus F sub G is greater than 0. So the normal is greater than the F sub G. That's good. 5 minutes. I don't think this is quite enough to do the next thing. Let me take a couple quick questions. How people are doing here. I think the blood is draining out of people's hands from having their hands up. Lauren, how's it going?
Hi, can we still ask about the midterm?
Yeah, sure.
Okay, I just had a quick question about the format. So I noticed that in the second one, the second question, you put acceleration in the simplifying diagram area, and like if we were to put it in the represent mathematically instead, would that like be wrong because we didn't put it in the simplifying step, or does it still sort of translate through the whole process?
You mean the arrow that shows which way it's accelerating? You put that in the represent mathematically, or
I just put like acceleration was like negative 9.8 and represent mathematically.
Yeah, when you plug in numbers. So yeah, that makes some sense. But yeah, you want to state somewhere in the simplify, you want to state like it's free fall or projectile motion, or A sub y is G. I think
okay.
That's kind of what you're looking for in the simplifying diagram. So try to figure out what representation you've got, right? You're doing projectile motion.
Right, okay.
Okay.
That's it then, thank you.
Okay, sure. Yeah, this marking scheme is a little bit, takes a bit of getting used to. Uncio?
The second midterm question, it says to define the origin as like your starting place. I was wondering, instead of that, we could have just used like delta dy or delta dx and delta dy to represent the change in something instead of specifically mentioning an origin.
Yeah, that makes sense. Yeah, and then but the height of the cliff is going to be
negative as
the
long
absolute
as
value, negative of delta dy. Yeah, that makes sense.
Okay, thank you.
Yeah, so my markers are instructed that there is more than one way to solve these problems, and as long as you've structured your thing using these 4 steps and you've gotten set it up correctly and done it right, then you get full points. It's just a matter of not making mistakes. I guess the only thing is that you might make a bad mistake and then another mistake that cancels out the first mistake and end up with the right answer. That's that's not going to be full points because you get points for doing correct things. Michael Ip.
Hi, Professor.
Hi.
I have a question regarding towards like the midterm question 1.
Yeah.
So since there are like 2 like ways to solve the question, and then I did not assume that the object was moving or like the object is stationary, but then I got the correct answer for like the object is moving and just didn't write the assumption. So in that case, will I just get minus 0.5 marks off?
Yeah. So that's a question about this rubric. That's a good one. Yeah, I think that writing the assumption, you have to, so the assumption that you're making is that the kinetic friction is to the left, right? It's not quite clear from the setup of the problem that kinetic friction has to be the left. You have to have a velocity to the right in order to have kinetic friction to the left. So that to me was an assumption. So yeah, I think it's half a point. All righty. I'm going to do the bank curve example on Friday. The other thing we're going to do on Friday is another TeamUp quiz. So make a plan during lecture to get together with your practicals group, same as we did last Friday. Again, I'm going to post 3 multiple choice questions on something called TeamUp Quiz Module 3 on Chapter 5 stuff. And if you can't make the TeamUp quiz during class, it could be done either with your pod or on your own at any time over the weekend. So I will see you guys on Friday. And I'm going to turn off the recording, and then I can go to the hands here. It'll do stuff.